Okay, let's dive deep. Today, we're talking about something that might sound a bit intimidating, numerical linear algebra.
Hmm.
But trust us, this isn't just, abstract math for the classroom.
Not at all.
This is really the engine under the hood of so much stuff, like simulating fluid flow, or even figuring out why Google ranks pages the way it does.
That's exactly right. And for this deep dive, our source is this really insightful lecture series by Professor Yousef Saad from the University of Minnesota.
Okay.
And what's great is how he traces the whole history and evolution of the field. It shows how these core math tools developed decades ago for classic science problems
Yeah.
are now just absolutely fundamental to this huge world of data science we live in.
So our mission here then is to sort of unpack the essential ideas of numerical linear algebra, NLA, let's call it NLA,
But LA, yeah.
and show how these powerful tools really provide the foundation for solving complex problems, whether it's traditional science or, modern data stuff.
And you could really see the shift over the last, 70 years? From solving huge equation systems to analyzing networks, and now, bang, right into data analysis and machine learning.
It's kind of amazing to think back to the start. The lecture mentions a paper, was it 1953?
Yeah, around then.
With a title like Solving Linear Systems Can Be Interesting, which I guess sounded a bit quirky then.
Maybe a bit understated. But you fast forward 70 years, and you look at how these same ideas underpin machine learning. Well, you could definitely say linear algebra and machine learning is very interesting now.
Huh, understatement of the century, maybe. Okay, so let's get basic for a second. What exactly is numerical linear algebra?
Well, you can think of NLA as the practical computational side of linear algebra.
Oh, okay.
It's all about developing and, more importantly, using computational methods to solve problems involving matrices and vectors. But the key is doing it efficiently and reliably on actual computers,
Especially when things get big.
especially when they get massive.
And massive seems key, right?
Yeah.
Because real world problems often generate these huge systems, but you mentioned they're often sparse. What does that mean exactly?
Sparse just means most of the entries in the matrix are zero, like overwhelmingly zero.
And why is that so common?
Well, it comes up naturally because in most real systems, things aren't directly connected to everything else.
Ah, okay.
Think about structural engineering. A beam only directly affects the joints it's physically connected to, or an electrical circuit, a wire usually just connects 2 points.
Gotcha.
So when you write down the matrix describing these connections, you get tons and tons of zeros.
And NLA takes advantage of that.
That's the crucial insight. You design algorithms that don't store the zeros, don't do math with the zeros. It's the only way we can tackle the enormous scale you see in, say, reservoir simulation or analyzing complex networks.
Right, otherwise it's just impossible computationally. So, okay, you have this huge sparse system, the classic AXB problem. You need to find X. How do you do it without trying to invert that giant A matrix?
You almost never invert it directly. You use what are called iterative methods.
Iterative, meaning step by step.
Exactly. You start with a guess for the solution, maybe just a vector of zeros, and then you refine it in steps. Each step gets you, hopefully, closer to the true answer.
Were there older methods for this?
Yeah, historically, people use simple methods like Jacobi or Gauss-Seidel. They're sort of relaxation methods.
Are they still used?
Not usually on their own for the final solution anymore, not for really big problems. But the idea behind them is still super valuable. They often get used as components like smoothers or preconditioners inside more advanced methods.
Okay, so what are these more advanced techniques?
A really core idea the lecture introduces is projection methods.
Projection.
Yeah, the insight is like, okay, searching the whole massive space for the exact solution is too hard.
Yeah.
What if we look in a smaller, more manageable subspace?
Ah, limit the search.
Right. You carefully build this smaller space,
Huh.
and then you kind of project the original problem onto it. You use mathematical rules, often orthogonality, like finding the closest point to get the best possible approximate solution just within that limited space.
And this leads to, I think I've heard of Krylov's subspace methods.
Exactly. You're jumping ahead. That's perfect. That's where the real power for large, sparse systems lies.
Okay, tell me about Krylov.
Krylov methods, like Arnoldi or Lanczos, are these really clever, systematic ways to build a sequence of these subspaces. You start with a vector, and then you keep multiplying it by the matrix A.
A times the vector, A times that result, and so on.
Precisely. A squared, a cubed, times your starting vector. The space spanned by these vectors forms a Krylov subspace. And as you make this subspace bigger, step by step, It tends to contain better and better approximations to the actual solution of XB.
And the beauty is,
The beauty is, all you ever need to do is matrix vector multiplications, a times sum vector.
which is fast for sparse matrices.
Exactly. Because you only deal with the non-zero entries. You never have to form the whole dense matrix A squared or anything like that.
Clever. And you mentioned Arnoldi and Lanczos.
Yeah, Arnoldi is the general method. Lanczos is a specialized version, even more efficient. But it only works if your matrix A is symmetric.
Okay. And the conjugate gradient method. That one comes up a lot. CG.
CG is probably the most famous iterative method of all. It's specifically for systems where A is symmetric and also positive definite, a property related to energy in physical systems, often.
Right.
It actually comes out of the Lanczos process. It's got this really elegant structure and often converges very quickly. It dates back to those early 1950s papers we mentioned, developed independently by Stiefel and Hestines, a real cornerstone.
Okay, so that's ACX is B. Huge area. What about the other fundamental problem? AX is the eigenvalue problem.
Ah, yes, eigenvalues and eigenvectors.
This always felt, I don't know, more abstract to me.
It can feel that way, but they capture something really fundamental about the matrix A, about the linear transformation it represents.
Which,
They represent special directions, the eigenvectors. X, where applying matrix A just scales the vector by a factor root, the eigenvalue. It doesn't change the vector's direction.
okay, like finding the natural axes of the transformation.
That's a good way to think about it, like finding the natural frequencies or modes of vibration in a structure, or maybe the principal directions of variation in a data set. They reveal the intrinsic properties, the sort of essence of the matrix A.
So why do we need to find this essence in the real world? Where does it show up?
Oh, all over the place, often unexpectedly. Take Google's PageRank.
The search ranking.
Yeah, the core idea behind ranking web pages based on how they link to each other, that can be formulated as a massive eigenvector problem.
Really? How?
You build a huge matrix representing the link structure of the web. The most important eigenvector of this matrix, the one corresponding to the largest eigenvalue, basically tells you which pages are most important or which pages you'd end up on most often if you just randomly clicked links.
Whoa. Okay, that's a serious aha moment. PageRank is an eigenvector problem.
It is a gigantic one. But you also see eigenvalues popping up when you analyze the stability of power grids or when you model dynamical systems like how diseases spread.
How so?
Often the change in a system over time is described by an equation like DIT, A. The solution involves the eigenvalues of A. They tell you if the system will grow, decay, or oscillate. They govern the long-term behavior.
Okay, so finding them is important. How do you do it for these huge, sparse matrices we keep talking about? Same tricks as AXB.
Pretty much. Again, iterative methods and subspace approaches are key. There are simpler ideas, like the power method, which can find the eigenvalue with the largest magnitude.
Just repeatedly multiply by A.
Basically, yeah.
Yeah.
But for finding other eigenvalues, or for more robustness, the Arnoldi and Lanczos methods come back again.
How do they work for eigenvalues?
The idea is similar. You build that Krylov subspace using matrix vector products. Then you look at the projection of the matrix A onto that small subspace. The eigenvalues of that small projected matrix turn out to be really good approximations to some of the eigenvalues of the original huge matrix A.
They're called Ritz values, right?
That's the term, yes. Ritz values. They approximate the true eigenvalues.
But again, you can't just keep building that subspace forever, can you? Memory runs out.
Exactly. That's
Yeah.
a major practical issue. So modern eigenvalue solvers for large problems use clutter tricks. One is restarting.
Restarting.
Yeah, you run Arnoldi or Lanczos for a certain number of steps, build up a subspace, get some Ritz value approximations, then you kind of prune the subspace, you shrink it back down, keeping only the information that seems most promising for the eigenvalues you want, and then you continue building it up again.
Ah, like focusing the search.
Precisely. And you also use techniques like deflation. Once you've accurately found an eigenvalue and its eigenvector, you mathematically remove it from the problem so the method can focus on finding the remaining ones.
So it's these combinations, Krylov subspaces, restarting, deflation, that makes solving huge eigenvalue problems actually feasible.
Absolutely. That's what's inside the black box in a lot of scientific and engineering software.
Okay, shifting gears a bit, but maybe related. The lecture talks a lot about graphs, calls them the language of connections. How do graphs fit into this NLA picture?
Graphs are fundamental. Nodes, vertices connected by edges or links, they're just a natural way to represent relationships. Social networks, molecules, the internet, road networks.
All graphs.
Right. And the connection to NLA is immediate and powerful.
Yeah.
You can represent a graph using a matrix.
Like the adjacency
That's
matrix.
the most common one. And entry A is 1, or maybe some weight if node I is connected to node J and 0 otherwise.
And then properties of this matrix tell you things about the graph's structure.
Exactly. For instance, if you can rearrange the rows and columns of the adjacency matrix so it breaks into independent blocks along the diagonal,
Yeah.
that tells you the graph isn't fully connected. It has separate components.
Yeah.
So analyzing the matrix structure with NLA tools gives us really deep insights into the network's connectivity and overall shape.
What kind of insights can you get beyond just connectivity?
A big one is centrality. Trying to figure out which nodes or edges are the most important or influential in the network.
How do you define important?
Well, there are different ways, which is interesting in itself. Maybe importance just means having the most direct connections, that's degree centrality.
Simple enough?
Or maybe it's about being a crucial bridge on the shortest paths between many other pairs of nodes, that's between D-ness centrality.
Okay, being a bottleneck.
Sort of, yeah. And the lecture mentions Banachit's centrality, which is a bit more subtle. It captures the idea that a node is important if it's connected to other important nodes. It's like influence spreading recursively.
That sounds like eigenvalues might be involved again.
It often is. Many centrality measures end up being related to eigenvector problems on the graph's matrix representation.
And the graph Laplacian, that term came up, sounds significant.
It really is, especially for undirected graphs. The Laplacian matrix, usually written LDW, where D is the diagonal matrix of node degrees, and W is the adjacency matrix.
Okay, D minus W.
This matrix L has some beautiful properties. It's always symmetric and positive, semi-definite. And its eigenvalues tell you a lot.
Like what?
For one, the number of times 0 appears as an eigenvalue tells you exactly how many connected components the graph has. If the graph is fully connected, 0 is an eigenvalue only once.
Huh, neat.
And maybe even more importantly, there's this quantity x transpose LX, where x is a vector assigning a value to each node.
Yeah.
This quadratic form measures how smooth the values in x are across the edges of the graph. If connected nodes have very different x values, Lx will be large. If they're similar, it's small.
So it measures local variation.
Exactly. It connects the matrix algebra directly to concepts like diffusion, vibration, or potential energy on the network. It's a super important tool.
So graphs and matrices are really two sides of the same coin in many ways.
Right.
Where do we see the applications, especially thinking about that bridge into data science?
Oh, everywhere. Markov chains, for instance. These model systems moving between states randomly based on probabilities.
Like weather patterns or maybe stock prices.
Could be. The whole system is described by a transition matrix P. And finding the long-term probabilities of being in each state the stationary distribution is, guess what?
An eigenvector problem.
An eigenvector problem, PRE. PageRank is actually a great example of a massive Markov chain on the web graph.
It keeps coming back to eigenvectors.
It does. Another huge area is computational graphs.
How are those used?
They're used to represent complex calculations, like function evaluations, showing all the intermediate steps and dependencies. They're absolutely central to modern machine learning,
For neural networks?
especially for training neural networks. Calculating the gradients you need for optimization that's done using backpropagation, which is essentially an algorithm for efficiently computing derivatives by traversing this computational graph. The graph structure is the computation structure.
Wow, okay, so graphs help us understand the computation itself. What about analyzing data using graphs, like grouping similar things?
Right, that's clustering. A fundamental task in unsupervised learning, finding groups in unlabeled data.
How do graphs help there?
You can build what's called an affinity graph from your data. Each data point is a node. You draw an edge between two nodes if the corresponding data points are similar, maybe close to each other in some high-dimensional feature space.
Okay, build a network of similarity.
Exactly. And then the problem of clustering the data becomes a problem of partitioning this graph, finding groups of nodes that are tightly connected internally, but sparsely connected to other groups.
Like finding communities in a social network.
Same idea.
Yeah.
And NLA techniques, particularly spectral methods using the eigenvectors of the graph Laplacian we just talked about, are very powerful tools for finding these graph partitions, these clusters.
And image segmentation, is that related?
Very similar concept. You can think of an image as a grid of pixels. You build a graph where each pixel is a node.
Okay.
Then you connect nearby pixels with edges. And the weight of the edge depends on how similar the pixels are, maybe in color, texture, brightness. Then segmenting the image into meaningful regions, like separating an object from the background, becomes, again, a graph partitioning problem. You want to cut the fewest or weakest edges to separate the graph into pieces. Spectral methods based on the Laplacian are often used here too.
It's amazing how these core ideas, matrices, eigenvalues, graphs keep reappearing. This clearly shows that bridge to data science you mentioned. How does NLA specifically tackle common data science problems?
Well, a massive area is dimension reduction.
Reducing dimensions. Why?
Because real-world data images, text, genomic data often has thousands, even millions of features. It lives in this incredibly high-dimensional space.
Hard to work with.
Exactly. Hard to analyze, hard to visualize, prone to the curse of dimensionality. So dimension reduction aims to find a lower dimensional representation, like projecting it down onto a 2D plane or a 3D space, while still preserving some important structure or information from the original data.
And PCA, principal component analysis, is the classic way to do this, right?
It's definitely the most well-known linear method. The core idea in PCA is to find the projection directions, the principal components that capture the maximum variance in the data.
Why variance?
Because variance is often a good proxy for information content. Directions where the data spreads out the most are often the most interesting or informative.
And how does NLA find these directions?
Mathematically, these principal components turn out to be the eigenvectors of the data's covariance matrix, or relatedly, the singular vectors of the data matrix itself. It's fundamentally an eigenvalue singular value decomposition problem.
And it's unsupervised, doesn't need labels.
Correct. PCA just looks at the spread of the data itself. You could use it to, say, take high-dimensional images of digits and project them onto 2D to see if the different digit classes naturally separate out.
Are there other ways, maybe using those graphs we talked about?
Yes, definitely. And they offer a different philosophy.
Yeah.
Methods like eigenmaps or locally preserving projections, LPP. These methods first build that similarity graph from the data points we discussed earlier. Then they find a lower dimensional embedding, a projection, that specifically tries to preserve the local neighborhood structure defined by that graph.
So if 2 points were close in the original space, connected by an edge, they should stay close in the reduced space.
That's the goal. They often use the graph Laplacian again. The eigenvectors of a Laplacian corresponding to the smallest eigenvalues, excluding the very first 0, 1, tend to capture these smooth, slowly varying patterns across the graph, which gives you the embedding directions that respect local structure.
So PCA maximizes global variance, while these graph methods focus on preserving local relationships.
That's a good way to summarize the difference in philosophy, yeah. LPP gives you an explicit linear map, while eigenmaps is more implicit or nonlinear.
When you do this, though, how do you pick the right lower dimension? Should it be 2D, 3D, 10D?
That's a really tough and crucial question in practice. The intrinsic dimension of the data.
How do you estimate it?
One common way is to look at the eigenvalues you get from PCA, or singular values. You plot them in decreasing order of the spectrum and look for an elbow, or a point where they drop off significantly.
Suggesting the remaining dimensions don't capture much variance.
Right. The number of eigenvalues before the drop-off gives you an estimate of the data's numerical rank or intrinsic dimension. But you always need to pick a threshold for what counts as significant, and that can be subjective or data-dependent.
Tricky.
The lecture also mentions a more advanced concept, looking at the spectral density, or density of states.
Density of states.
Yeah, it's basically a histogram showing how the eigenvalues are distributed across the spectrum. Instead of just counting how many are large, you look at the overall shape of the distribution. It's a concept borrowed from physics, but it can potentially give more robust information about the data's structure and dimensionality. There are NLA methods, like the kernel polynomial method or using Lanczos with quadrature rules to estimate this density efficiently.
Interesting. Okay, so that's unsupervised learning finding structure. What about supervised learning, where you do have labels, like classifying those digit images?
Right. So now you have your training data images,
Right.
and for each one you know it's a 3 or a 7 or whatever. The goal is classification. Learn a rule from this labeled data to predict the correct label for a new unseen image.
How does NLA come into play there?
Well, many classification methods have linear algebra at their heart. The simplest are linear classifiers.
Trying to draw lines between classes.
Exactly. Trying to find a hyperplane, a line in 2D, a plane in 3D, you get the idea that separates the data points belonging to different classes. Methods like support vector machines, SVMs, are famous examples that try to find the best separating hyperplane, the one with the maximum margin.
But what if you can't draw a straight line or plane to separate them? If the data is all mixed up?
That's where the kernel trick comes in, which is super clever. Yeah. The idea is you use a kernel function to implicitly map your data into a much higher dimensional space. Often, data that's tangled and non-separable in low dimensions becomes nicely, linearly separable in some higher dimensional space.
You map it somewhere else where it's easier to separate?
Sort of, but you don't actually do the mapping explicitly. The kernel function lets you compute the necessary dot products and distances in that high-dimensional space without ever actually calculating the coordinates there. It's computationally very efficient. It's like taking tangled strings on a table and lifting them into the air so you can easily slide a piece of paper between them.
That is clever. Any other NLA-based classifiers?
Another important one is Fisher's linear discriminant analysis, or LDA.
LDA. How's that different from PCA?
Unlike PCA, which ignores labels, LDA specifically uses the class labels. Its goal is to find a projection direction, a lower dimensional space, that simultaneously maximizes the distance between the means of the different classes,
Pushing the groups apart.
while minimizing the scatter, or spread, within each class.
Keeping each group tight.
Exactly.
Yeah.
So it's explicitly trying to find the view that makes the classes as distinct and well separated as possible using the label information.
Makes sense. And of course, we have to mention neural networks and deep learning.
Absolutely. They're dominant in many areas now. At its core, training a deep neural network is a huge nonlinear optimization problem.
Finding the right weights.
Finding millions, sometimes billions, of weights and biases in the network layers so that the network learns to approximate the function you want, like mapping input image pixels to an output digit label.
And NLA is involved how?
The training process relies heavily on efficient matrix and vector operations for the forward pass, calculating the output, and especially for the backward pass, calculating gradients via backpropagation. Remember those computational graphs?
Yeah.
NLA libraries are the workhorses doing those massive matrix multiplies and other operations efficiently on GPUs. It's computationally super expensive, but incredibly effective for complex tasks.
So we've covered a lot from AXB and eigenvalues in classical science through graphs as this connecting language and right into core data science tasks like dimension reduction and classification. What about more advanced stuff looking ahead?
Well, one interesting technique the lecture touched on is graph coarsening.
Coarsening, making it rougher.
Sort of. The idea is to create a sequence of smaller, simpler graphs that approximate the original large, complex graph. Think of it like generating lower resolution versions of your network that still capture its essential structure.
Okay, why would you want a lower res version?
Speed. Computations on smaller graphs are much, much faster.
Ah,
This idea actually comes from scientific computing, where it's used in methods like algebraic multigrid, AMG, to solve those AXB systems super efficiently. You solve an approximate version of the problem on a coarse grid, then use that solution to help you find the solution on the finer grid.
and this applies to data science graphs too.
Yes, it's being adapted now. For instance, if you want to compute graph embeddings, those low-dimensional representations for truly massive networks, billions of nodes, doing it directly can be impossible.
Too big.
Right. So methods like HARP or MILE use graph coarsening. They create a smaller version of the graph, compute an embedding for that much faster, and then carefully map or refine that embedding back up to the original huge graph. It's a way to make embedding scalable.
That's really neat. It feels like the field is definitely not standing still. It's constantly adapting, especially with all these demands from data science.
Oh, absolutely. It's incredibly dynamic right now. Professor Saad emphasizes how much the landscape has shifted, especially in just the last, say, 5 or 6 years. The synergy between classical NLA techniques and the new types of problems and massive scale coming from data is driving a lot of innovation.
And there are more resources now.
Tons. Lots of software, online courses, papers. It reflects this real boom in interest in application.
It's just powerful to see how a field that maybe started with someone thinking, solving linear systems could be interesting,
Yeah.
has evolved to be so completely central to our modern data-saturated world.
It really is. It makes you think of that quote, I think attributed to Alexander Graham Bell.
Which one?
Something like, when one door closes, another opens. But we often look so long and so regretfully upon the closed door that we do not see the one which has opened for us.
How does that connect?
Well, the new challenge is the sheer scale, the different structures in data science. Those are the new doors opening for NLA. And by looking through them, applying and adapting these powerful tools, we're finding solutions and creating technologies that, weren't even really imaginable decades ago. It's about embracing the new problems.
Okay, so let's try to wrap this deep dive up. We've journeyed from the roots of numerical linear algebra and classical scientific computing solving equations for physics, for engineering,
Right, the traditional AXB and eigenvalue problems.
through understanding the power of graphs as this language for connections,
Networks everywhere.
and landed squarely in the world of modern data science. We've seen NLA is essential for dimension reduction, for clustering data, for classification, for the engines behind machine learning.
It really is the fundamental machinery. It provides the computational tools and, just as importantly, the conceptual frameworks thinking in terms of vectors, matrices, eigenvalues, graphs that let us extract meaning and solve problems when faced with huge data sets and complex interconnected systems.
And for you listening, think about the connections you encounter constantly. The search results you get, the friends suggested on social media, the products recommended to you online.
Mhm.
Underneath the surface of many of these systems, you'll find representations based on graphs and matrices being manipulated and solved using the kinds of NLA techniques we've been talking about.
And maybe the final thought to leave you with is this.
Yeah.
Really getting a handle on these foundational numerical tools, understanding linear algebra not just as abstract math, but as a practical problem-solving toolkit.
Right.
It can genuinely unlock new ways of seeing the world and tackling challenges.
There's just immense potential, as Professor Saad suggests, to make a real impact by looking at problems, old or new, from this perspective. Being able to model things using matrices and graphs, and knowing the methods exist to actually solve those models computationally. It's a powerful combination. It's about seeing the underlying structure that linear algebra reveals,